about bond association energy. So again, if you have notes, you'll have this handy dandy chart that's on there. And if you don't, and I might end up redoing this whole thing. So I have notes, and I just write on the notes, which is going to be so not me. But, so the rule here is we're going to do a little formula. So remember that, the sum? The sum of the bonds broken minus the sum of the bonds formed. You don't have to ever show that little sigma sign. I just like writing it. It's really fun to write. All right, trying to figure out lighting. So let's just do one. So it says we have our equation, hydrogen plus chlorine, and we go to 2HCl. Yeah, and so H2 would mean hydrogen, hydrogen. Cl2 is chlorine, chlorine. And HCl would mean we have an HCl bond and another HCl bond. So we're going to look at these and find the numbers. So hydrogen, hydrogen is 436 kilojoules per mole, which means per bond. A chlorine-chlorine bond, so you'd find chlorine and where chlorine meets, is 242 kilojoules per mole. Oh, this is showing up much better, isn't it, than the colored markers. So we can start all over. And HCl. So we find hydrogen and chlorine, so in that first row coming over, and that would be 432 kilojoules per mole. And by the way, these tables come from Coates' book, which I actually did put on your web, on our MyMHCC. I was able to post the book. It's the entire book. That it's actually a book we used for many years for 221, 222, and 223. All right, there are going to be two of these, so we're going to have two HCl's times this. And is the bond broken? These are the bonds broken. So for those of you, when we did this in 221, we did it a different way. We used a different chart, and it wasn't based on bonds broken and bonds formed. It was based on somebody in lab using much fancier than our coffee cup calorimeter, but a styrofoam coffee cup, and doing calorimetry and figuring out values for every single compound. Here we're going to actually be breaking things into individual bonds. So my first example is very simple, and so it might look the same, but the answers do not actually come out the same. And the other thing that was different is we always would do products minus reactants, and half of you would get it wrong. For 25 years, half of you would get it wrong because you want to just go forward in the reaction. Well, now you get to go forward. Where half of you are going to lose points is you're not going to label. So it is bonds broken, and then these are the bonds formed. So you just set up the equation, and then you just write these. So these are added together on each side, and then we subtract our bonds formed. The thing is you would need to label. So this is my hydrogen-hydrogen bond. Now, how I have it labeled, I'm actually okay with you doing it that way. So let's just go with that. All right. And we punch it in, and thankfully I already did it because I don't have a calculator with me, and I got negative 136 kilojoules. Now, if we did it the old way, we might get a slightly different answer, and the reason is these are based off of numbers the gnomes gave us. Because how the heck can you go in and break a bond and measure the kilojoules that were given off? So the way we did it in lab was we used a calorimeter and we used a thermometer, and we had a whole bunch of heat loss and a whole bunch of experimental errors. Well, the gnomes are our good friends, and the gnomes went in and actually are able to measure the strength of the bonds and the length of the bonds, and they're able to give us these wonderful charts. And so the numbers come out similar. You're going to have a question in your first worksheet where you're going to calculate it both ways, and Yeah, it's just different methods, and I like Gnome's numbers, it's easier. All right, we're gonna do a second one. Let's go for it. And I need an eraser. All right, so this one tells us, so you want to write your formula, bonds broken. So for those of you who know me, you know I'm a stickler for you have to tell me what you're doing. Because I need to know that you got the idea, minus bonds broken. And for those of you new to me, you probably heard that I'm a stickler for that I need to see your work. And this is great training because when you take physics, your physics teacher will send me much love and gratitude because you showed this. Okay? So in this case we have H2 plus C3H6, and it says we're going to C3H8. All right, so we need to draw these. This is hydrogen, hydrogen. This is going to be 3 carbons hooked together. The next video is about Lewis structures and drawing them, and then next week we spend a lot of time on organic chemistry. So you'll become really good at this. Carbons make 4 bonds. Carbons are a 4A. Carbons want to be 8 valence electrons. They make 4 bonds. They can make 4 single bonds. They can make a double and a single. Hydrogens only will make 1 bond. So we have 3 hydrogens, 4, 5, 6, and we've run out of hydrogens. Now I know the answer, so I get to do a shortcut here. So the only way this can work out and the carbon can have 4 bonds is I need a double bond between those 2 carbons. So my first carbon here has 4 single bonds around it. My second carbon has a single, a double, and then another single. Anyway, just trust me on this. This is why we're going to label our work. Here when we get to C3H8, I make my 3 carbons in a row. And I have enough hydrogens that everybody gets their own hydrogens. When we do a lot of this stuff, we're going to do a north, south, east, west grid because it makes it easy to teach it this way. And then I'll be showing you next week how more it really looks. But each carbon is making 4 single bonds, and I have 8 hydrogens around it. So bonds broken. I have a hydrogen-hydrogen bond. So my hydrogen-hydrogen bond, I also have a carbon double bond. So here we're going to label, I have a carbon double bond that doesn't show up on the other side. I have 1 hydrogen-hydrogen bond that doesn't show up on the other side. Now the carbon-hydrogen bonds are on both sides. It's just a different number of them. So I have 1 of these and I have 1 of these. So here I have 6 carbon-hydrogen bonds. And over there I now have 8. So you can go through every single bond, or you can realize you just have 2 new carbon-hydrogen bonds. Let me put the 2 in front, sorry. We also have another bond, which is the carbon-carbon bond. Here I have 1. Here suddenly I have 2. So I have 1 new carbon-carbon bond. So I had 1 hydrogen-hydrogen bond, 1 carbon double bond. Those are gone. 6 of the carbon-hydrogen bonds are still there, so I don't worry about there's no change there. So now we just have to look up the numbers in the chart. 436 kilojoules plus the carbon double bond is at the bottom of your chart, and that's 610 kilojoules. Those are my bonds that are broken. And then I'm going to subtract, instead of the arrow, 2. And as long as you have this up above, exactly what you did, you write out your reaction, the way we always did before. You draw out your molecules, you write down what your bonds are. You're going to show this very clearly if you want to get 100%, and you all want 100%. There's no reason you can't all have 100%. It's all take home. And then the carbon-hydrogen bond, which is 413. And a carbon-carbon bond, so 346. And it does say kilojoules per mole. This would be the 2 moles, and this would be kilojoules per mole. You can write the word in moles, but as long as it's lined up like that, and we punch it in, and what I have from previous years is our answer is negative 126 kilojoules. Now, I know some of you, and you will do this math, and hopefully I have it right. I don't have any red mark in there, so we're going to assume everything's great.